Hello and welcome. Today, we're embarking on a fascinating journey into the world of quantum thermodynamics. This field sits at the intersection of two of the most successful theories in physics, quantum mechanics and thermodynamics. Our goal is to understand how the fundamental laws of thermodynamics, which govern energy and entropy in the macroscopic world, are modified and enriched when we apply them to systems at the quantum scale. By the end of this lesson, you will be able to define key quantum thermodynamic concepts, understand the role of quantum effects like coherence, and explore advanced topics like quantum engines and fluctuation theorems. This isn't just an academic exercise. Quantum thermodynamics is crucial for developing future technologies, from ultra-efficient quantum computers to novel energy harvesting devices. So let's dive in. To begin, we need to establish the language of quantum mechanics. In the quantum world, the state of a system is described by a mathematical object. For a pure state, this is a state vector, often written as a ket vector, like this. This vector contains all the information about the system. However, in thermodynamics, we rarely deal with pure states. Systems are almost always in a mixture of different states, either because we don't know the exact state, or because the system is interacting with its environment. For these mixed states, we use a more powerful tool called the density matrix, represented by the Greek letter rho. The density matrix is a square matrix that provides a complete statistical description of a quantum system. It's a weighted average of the pure states the system could be in. Mathematically, it's defined as a sum over possible pure states, where P_i is the probability of finding the system in the pure state SI_i. The density matrix is the central object in quantum thermodynamics. It allows us to calculate the average value of any physical quantity, like energy or momentum, for a mixed state. The average value, or expectation value of an observable A, is given by the trace of the product of the density matrix and the operator A. The trace of a matrix is simply the sum of its diagonal elements. So, to recap, we use state vectors for pure states, but for the mixed states common in thermodynamics, we use the density matrix, RHO, which is a statistical description of the system. Now that we have the density matrix, we can define the quantum version of a fundamental thermodynamic quantity, entropy. In quantum mechanics, entropy is quantified by the von Neumann entropy, named after John von Neumann. Just as classical entropy measures the uncertainty or disorder in a classical system, the von Neumann entropy measures the uncertainty or mixedness of a quantum state. The formula for von Neumann entropy is S of rho equals minus the trace of rho times the natural logarithm of rho. This is the quantum analog of the classical Gibbs entropy formula. Let's look at two important properties of this entropy. First, for a pure state, the entropy is zero. This makes sense, as a pure state is perfectly known and has no uncertainty. Second, for a maximally mixed state, where all possible states are equally likely, the entropy is at its maximum. This represents the highest possible uncertainty. So the von Neumann entropy is a measure of how mixed a quantum state is. A pure state has zero entropy, while a maximally mixed state has the highest entropy. A key concept in thermodynamics is thermal equilibrium. In the quantum world, this is described by the Gibbs state. The Gibbs state, also known as the thermal state, is the state a system reaches when it's in equilibrium with a heat bath at a certain temperature. It's the quantum analog of the classical Boltzmann distribution. It tells us the probability of finding the system in a particular energy state. The formula for the Gibbs state is RHO sub T H equals 1 over Z times e to the power of minus beta H. Here, H is the system's Hamiltonian, which represents its energy. Beta is 1 over K underscore BT, where K underscore B is Boltzmann's constant, and T is the temperature. Z is the partition function, a normalization constant. The Gibbs state is crucial for understanding how quantum systems behave at finite temperatures. It's the starting point for many calculations in quantum thermodynamics. Now, what happens when a system is not in equilibrium? How does it get there? This process is called thermalization. Quantum thermalization is the process by which an isolated quantum system, starting from a non-equilibrium state, evolves over time to a state that looks like a thermal state. This is a deep and active area of research. The question is, how can a system that is fundamentally governed by the time-reversible Schrödinger equation end up in an irreversible thermal state? The answer lies in the system's own complexity. For a large, complex system, its own internal dynamics can act as a bath, causing it to thermalize. This is often described by the eigenstate thermalization hypothesis, or ETH. The ETH states that for a thermalizing system, the expectation value of an observable in any energy eigenstate is equal to the thermal expectation value at the corresponding energy. In simpler terms, the system's own energy eigenstates are already thermal. So to summarize, the Gibbs state describes a system in thermal equilibrium, and quantum thermalization is the process by which a system reaches this state, often explained by the eigenstate thermalization hypothesis. In the real world, systems are rarely perfectly isolated. They interact with their environment. This leads us to the concept of open quantum systems. An open quantum system is a system that is coupled to an external environment or bath. This interaction causes the system's state to evolve in a way that is not described by the simple Schrödinger equation. The environment can cause two major effects: dissipation and decoherence. Dissipation is the loss of energy from the system to the environment, like friction. Decoherence is the loss of quantum coherence, which is the ability of a system to be in a superposition of states. Decoherence is what makes the quantum world look classical. The evolution of an open quantum system is described by a master equation. A common and important example is the Lindblad master equation. The Lindblad equation describes the time evolution of the system's density matrix, RHO. The first term on the right describes the system's internal Hamiltonian evolution. The second term, the Lindblad superoperator L, describes the effects of the environment, including dissipation and decoherence. This equation is a cornerstone of quantum thermodynamics. It allows us to model how a quantum system interacts with a thermal bath, which is essential for understanding processes like thermalization and the operation of quantum engines. So to recap, open quantum systems interact with an environment, leading to dissipation and decoherence. Their evolution is described by master equations like the Lindblad equation, which are crucial for modeling realistic quantum thermodynamic processes. Now let's connect these quantum concepts to the familiar ideas of work and heat. In quantum thermodynamics, we need to be very precise about how we define these quantities. Work in quantum mechanics is defined as the energy transferred to the system by changing its external parameters, like the volume of a gas or the strength of a magnetic field. This is a coherent process, meaning it doesn't involve the environment. Mathematically, if the Hamiltonian H depends on a parameter lambda, the work done is the integral of the expectation value of the force, which is the derivative of the Hamiltonian with respect to lambda. So work is the integral of the expectation value of the derivative of the Hamiltonian with respect to the parameter lambda, d lambda. Heat, on the other hand, is the energy transferred to the system through incoherent processes, like interactions with a thermal bath. It's associated with changes in the system's entropy. The first law of thermodynamics still holds in the quantum regime. The change in the system's internal energy, delta U, is equal to the work done on the system, W, plus the heat added to the system, Q. This is a statement of energy conservation. A key difference from classical thermodynamics is that in the quantum world, work is not always a well-defined quantity for a single realization of a process. It can fluctuate. We'll explore this more when we discuss fluctuation theorems. To summarize, work is coherent energy transfer from changing parameters. Heat is incoherent energy transfer from a bath. And the first law of thermodynamics, delta U equals W plus Q, remains valid. Let's put these concepts into practice with a worked example. Consider a single quantum bit, or qubit, in a magnetic field. The Hamiltonian for this qubit is H equals minus mu times B times sigma underscore Z, where mu is the magnetic moment, B is the magnetic field strength, and sigma underscore Z is the Pauli Z matrix. The energy eigenvalues are E underscore up equals minus mu B, and E underscore down equals plus mu B. Let's say the qubit is in a thermal state at temperature T. The density matrix for this thermal state is ρHO underscore T H equals 1 over Z times e to the power of minus beta H. Now, let's perform a work process. We will slowly change the magnetic field from an initial value B underscore I to a final value B underscore F. The work done is the integral of the expectation value of the force. The force operator is the negative derivative of the Hamiltonian with respect to B, which is mu times sigma underscore Z. Since we are changing the field slowly, the system remains in a thermal state at each instant. This is called a quasi-static process. The expectation value of the force is the trace of rho underscore th times F. This calculation gives us mu times the hyperbolic tangent of beta mu B. Integrating this from B underscore I to B underscore F gives us the work done. W equals 1 over beta times the natural log of the ratio of the partition functions at the final and initial states. This is a classic result for quasi-static work. This example shows how we can calculate work in a quantum system by changing an external parameter in a controlled way. Just as classical thermodynamics has engines, quantum thermodynamics has quantum engines. These are devices that convert heat into work at the quantum scale. A quantum engine operates on a cycle, just like a classical engine. It absorbs heat from a hot bath, performs work, and rejects heat to a cold bath. A common model is the quantum Otto cycle, which is the quantum analog of the classical Otto cycle. The quantum Otto cycle consists of 4 strokes. 2 are isentropic, where the system is isolated and work is done by changing the Hamiltonian. The other 2 are isochoric, where the system is coupled to a hot or cold bath and heat is exchanged. The efficiency of a quantum engine is defined in the same way as a classical engine, the ratio of the work output to the heat input. Efficiency, ETA, is the work output divided by the heat input from the hot bath. A remarkable result is that the efficiency of a quantum Otto engine can exceed the classical Carnot limit if the working substance is prepared in a quantum coherent state. This is a direct consequence of quantum effects. This phenomenon, known as quantum advantage, shows that quantum engines can be more efficient than their classical counterparts. This is a major motivation for research in this area. So quantum engines are devices that convert heat to work at the quantum scale, and they can exhibit quantum advantage, potentially leading to efficiencies beyond classical limits. In the quantum world, thermodynamic quantities like work and heat are not always fixed values. They can fluctuate from one run of an experiment to another. Fluctuation theorems are a set of powerful results that relate the probabilities of these fluctuations to the change in the system's free energy. They provide a bridge between the microscopic, fluctuating world of quantum mechanics and the macroscopic, deterministic world of thermodynamics. One of the most famous is the Jarzynski equality. It states that the average of e to the power of minus beta w is equal to e to the power of minus beta times the change in free energy, delta F. This is a remarkable result. It connects the work done in a non-equilibrium process, which can be very different from the free energy change, to the free energy change itself, which is a state function. The Jarzynski equality has profound implications. It means that by measuring the work fluctuations in a non-equilibrium process, we can determine the equilibrium free energy difference between 2 states. Another important result is the Crookes fluctuation theorem, which relates the probability of doing a certain amount of work in a forward process to the probability of doing the negative of that work in the time-reversed backward process. These theorems are not just theoretical curiosities. They have been experimentally verified in various systems, from single molecules to quantum dots, and are used to measure free energy differences in biological systems. So, fluctuation theorems, like the Jarzynski equality, provide a fundamental link between microscopic work fluctuations and macroscopic thermodynamic quantities, allowing us to probe non-equilibrium processes. Now let's delve into a purely quantum phenomenon that has profound implications for thermodynamics: quantum coherence. Quantum coherence is the ability of a quantum system to be in a superposition of multiple states simultaneously. It's what gives quantum mechanics its unique power. In the density matrix formalism, coherence is represented by the off-diagonal elements. A state with non-zero off-diagonal elements is coherent. For example, a density matrix with non-zero elements outside the main diagonal represents a coherent state. If all off-diagonal elements are zero, the state is incoherent or classical. Coherence is a resource. It's like fuel that can be used to perform thermodynamic tasks that are impossible classically. For instance, coherence can be used to extract work from a single thermal bath, which is forbidden by the second law of thermodynamics for classical systems. This is a direct violation of the classical Kelvin-Planck statement. This doesn't mean the second law is broken. It means that coherence itself is a form of energy that must be accounted for. The second law is extended to include coherence as a resource. The challenge is that coherence is fragile. It's easily destroyed by interactions with the environment, a process called decoherence. This is why open quantum systems are so important. So quantum coherence, represented by off-diagonal elements in the density matrix, is a powerful resource that can be used to perform non-classical thermodynamic tasks, but it is fragile and easily lost to the environment. To formalize the idea of coherence as a resource, physicists have developed quantum thermodynamic resource theories. A resource theory is a mathematical framework for quantifying and manipulating a specific resource. In this case, the resource is quantum coherence. The theory starts by defining a set of approche operations. These are operations that can be performed without expending any of the resource. For coherence, these are called incoherent operations. Incoherent operations are those that do not create coherence. They can only destroy it or leave it unchanged. They are the cheap operations in this theory. Any operation that creates coherence is considered a resourceful operation and requires an input of coherence. The theory then defines measures of coherence. A valid measure must be non-negative, 0 for incoherent states, and non-increasing under incoherent operations. One common measure is the relative entropy of coherence, which quantifies the distance of a state from the set of all incoherent states. This framework allows us to answer questions like, how much coherence is needed to perform a certain task? How much coherence can be extracted from a given state? And how efficiently can we convert one form of coherence into another? So, resource theories provide a rigorous mathematical framework for quantifying and manipulating quantum resources like coherence by defining free operations and measures of the resource. The concepts of quantum thermodynamics are not just theoretical. They are being actively explored in laboratories around the world. Experimental realizations of quantum thermodynamic phenomena are a crucial part of the field. They allow us to test the theory and develop new technologies. A common platform for these experiments is a single trapped ion. In a trapped ion experiment, a single atom is held in place by electromagnetic fields. Its internal energy levels can be used as a qubit, and its motion can be used to store energy. Lasers are used to manipulate the ion state and perform measurements. Using this platform, scientists have successfully demonstrated a quantum auto engine. They use the ion's internal levels as the working substance and its motion as the piston. By applying laser pulses, they could perform the 4 strokes of the Otto cycle and measure the work and heat exchanged. This allowed them to calculate the engine's efficiency and verify the theoretical predictions. Other platforms, like superconducting circuits and nuclear magnetic resonance, are also being used to study quantum thermodynamics. These experiments are not only verifying the theory, but also pushing the boundaries of what's possible. So, experiments with systems like trapped ions are successfully realizing quantum engines and other thermodynamic processes, providing crucial validation for the theory and paving the way for new quantum technologies. Let's now turn to one of the most intriguing and active areas of research, the quantum Maxwell's demon. Maxwell's demon is a thought experiment from the 19th century that seems to violate the second law of thermodynamics. A tiny demon is imagined to sort hot and cold molecules, creating a temperature difference without doing any work. The resolution in classical physics is that the demon must acquire and store information about the molecules, and the act of erasing this information generates entropy, thus saving the second law. In the quantum world, the demon is a quantum system that can measure and control another quantum system. The question is, how does information relate to thermodynamics in this quantum context? This leads us to the field of information thermodynamics, which explores the deep connection between information, computation, and the laws of thermodynamics. A key result is that information can be used as a resource to extract work. A quantum demon can measure the state of a qubit in a thermal bath and, based on the measurement outcome, perform a feedback operation to extract work. The maximum work that can be extracted is given by the Landauer bound, which states that the work is equal to K_BT times the mutual information between the system and the demon. This shows that information is a form of energy. This has been experimentally realized using a single electron in a quantum dot. The electron's spin acts as the daemon's memory. By measuring the energy state of the electron and applying a feedback voltage, scientists were able to extract work from a thermal bath, demonstrating the power of information in the quantum regime. So the quantum Maxwell's daemon and information thermodynamics reveal that information is a fundamental resource that can be converted into work, a concept with profound implications for computation and energy. Let's conclude by looking at the current research frontiers and challenges in quantum thermodynamics. The field is rapidly evolving, with many exciting questions yet to be answered. One major challenge is scaling up. Most experiments so far have involved only a few qubits. The goal is to build quantum engines and refrigerators with many interacting particles. This involves understanding how thermodynamics emerges in complex, many-body quantum systems. It's a bridge between quantum thermodynamics and condensed matter physics. Another frontier is the study of non-equilibrium processes. While fluctuation theorems provide some insight, a comprehensive theory of quantum thermodynamics far from equilibrium is still being developed. This involves understanding how systems evolve and exchange energy and information when they are driven hard and are far from any thermal state. Finally, there's the quest for practical applications. Can we build quantum batteries that store energy more efficiently? Can we design quantum sensors that are more sensitive due to thermodynamic effects? These are the questions that will drive the field forward. The potential for quantum technologies that leverage thermodynamic principles is immense, from energy harvesting to quantum computing. So the future of quantum thermodynamics involves scaling up to many-body systems, developing a full theory of non-equilibrium processes, and translating these fundamental insights into practical quantum technologies. Let's quickly recap what we've covered today. We started with the fundamental language of quantum mechanics, the density matrix, and used it to define the von Neumann entropy. We then explored how systems reach thermal equilibrium through quantum thermalization and how they interact with their environment as open quantum systems. We defined work and heat in the quantum regime and saw how they combine in quantum engines and are described by fluctuation theorems. Finally, we delved into the purely quantum aspects, coherence as a resource, the framework of resource theories, and the profound connection between information and thermodynamics revealed by the quantum Maxwell's daemon. You are now able to define key quantum thermodynamic concepts, understand the role of quantum effects like coherence, and explore advanced topics like quantum engines and fluctuation theorems. This field is a vibrant and rapidly growing area of research, promising to revolutionize our understanding of energy and information at the most fundamental level. Thank you for joining me on this journey. To solidify your understanding, here are a few practice questions. Take a moment to pause the video and work through them. First, what is the key difference between a pure state and a mixed state in quantum mechanics, and which one is more relevant for thermodynamics? Second, how is work defined in quantum thermodynamics, and how does it differ from heat? Third, explain the concept of quantum coherence and its role as a resource in quantum thermodynamics. Now let's go over the solutions. For the first question, a pure state is described by a single state vector and has zero von Neumann entropy. A mixed state is a statistical mixture of pure states, described by a density matrix, and has non-zero entropy. Mixed states are more relevant for thermodynamics because systems are rarely perfectly isolated and are often in a statistical ensemble. For the second question, work is the energy transferred by changing external parameters of the system, like a magnetic field. It's a coherent process. Heat is the energy transferred through incoherent interactions with a thermal bath, and it's associated with entropy changes. For the third question, quantum coherence is the ability of a system to be in a superposition of states, represented by the off-diagonal elements of the density matrix. It's a resource because it can be used to perform non-classical thermodynamic tasks, such as extracting work from a single thermal bath or enhancing engine efficiency. I hope these questions helped you review the key concepts. Thank you again for watching.